Okay, perhaps we can start. So we are happy to have Bob Knighton, who will be giving a tutorial on the set of lectures that Professor Matthias Gaberdiel gave over last week on tensionless ADS safety. Over to you, Bob.
All right, great. Thank you. So first, I want to thank the organizers for giving me the opportunity to give this to give this tutorial. Obviously, it would have been good to be there in person, but the circumstances what they are, this is quite good. I also want to say it is so due to travel restrictions, I was supposed to be in Switzerland today, but I am stuck in North America. So it is 3:30 in the morning. So if I do say anything that's a bit nonsensical, feel free to call me out on it. That's probably just the weird hour.
I'm very sorry to hear that, and we are very sorry.
It's perfectly fine. It was just
yeah.
It's just the whole flight situation. Yeah.
Thank you very much.
Yeah, still very happy to be here. And so my plan today is to go over some of the things that Matthias was talking about, but due to the time or wanting to cover everything, sort of wasn't able to give a real deep dive on. So and sort of go on these things in much more detail. So for instance, I will start out talking about classical strings on ADS3, sort of give a very pedagogical overview of that. And in particular, I want to convince you that spectral flow, this sort of magical operation that acts on current modes, can actually be thought of just as a standard winding number, but for the case of ADS3. And then I'll give a brief review of quantum strings on ADS3. So in particular, this SL2R current algebra construction that you've already seen in Matthias's lectures, except go into a bit more detail. So in this case, spectral flow isn't just some winding thing, it's some automorphism of the algebra that gives you new representations. And I'll discuss in more detail the representations of the current algebra. So the representations and the actual string states that appear in ADS3. And then I'll go into some detail on this free field realization that shows up. So as you guys have seen it, this showed up for PSU 112 at level 1, and I'll be focusing on the part of the free field realization that that matters for just the SL2R half. Well, there seems to be a lag in my iPad. Hopefully that's not too bad. And then afterwards, if I, oh. I have stopped screen sharing somehow. Give me 1 second.
We can see the screen, but okay. Yeah, we can.
Yeah, it just disconnected. Okay, let me try something a bit different because I have had problems with my iPad, but I think I can get it to work. Like this.
Yeah, we can see your screen.
Okay, great. Yeah, sorry about that. Hopefully that doesn't interrupt anytime soon. Okay, so if I get to the end of talking about this free field realization and I still have some time left, I might talk about some covering map stuff. And then I plan to take the last 20 or so minutes just for general, maybe 20, 30 minutes just for general Q&A. So stuff about things that I'll say now or things that came up in Matthias's lecture that maybe people didn't get a chance to ask, or people have new questions that they didn't think of at the time. All right, so let's jump right in. So first I'll just discuss in general strings on ADS3. And this is all based on this paper from 2000 by Maldaceno Noguri, whose archive code I've listed here. And the basic starting point of studying ADS3 is to actually try to parametrize the manifold itself. So ADS3, as all anti-de Sitter spaces, can be seen as a hyperboloid in some Minkowski space with two time directions. So you consider Minkowski space with 2, 2 signature with coordinates x-1, x0, x1, and x2. And then you can consider some hyperboloid, which is given by this algebraic equation, just sort of taking the inner product of your coordinates under this metric and setting them equal to 1. And the surface, which we'll call ADS3, it's invariant under the full Lorentz transformations of R22, which we can also call SL2R as a group. Now, what makes ADS3 special is that this hyperboloid doesn't just have some SL2R symmetry. You can show that it's actually the group SL2R itself. And the way you can do this is you can group these coordinates into an object I'll call G, which is just some 2x2 matrix, whose entries are just some nice linear combinations of the coordinates. And if you take the determinant of this object, you see that it's just the left-hand side of this expression here. And so the statement that my coordinates in R22 lie on this hyperboloid is the same as saying that I have some 2x2 matrix whose determinant is equal to 1. And so the set of 2x2 matrices with real coefficients whose determinant is equal to 1 is just the group SL2R. And so we can make the identification that ADS3 is nothing more than the group manifold of SL2R. Now, of course, this isn't quite right. There is a bit of a subtlety, which is that this hyperboloid is actually not simply connected. And if you were to parametrize it, it would sort of look like this filled torus with some filled hyperbolic torus with a periodic time direction. So in particular, you have to consider the universal cover of this surface, but that's a detail that's not going to matter so much. It just means when you parametrize it in terms of some coordinate system, you have to take a time coordinate which is non-compact. And so to recast this into coordinates you guys have probably already seen when talking about ADS, you can parametrize all possible solutions to this algebraic equation by introducing some new coordinates, t, rho, and phi, and then defining your x variables in terms of these new coordinates as follows. And if you then write out the metric of R22 in terms of these coordinates, you get what looks like the metric of ADS3 in global coordinates, where now I have some time coordinate which goes from negative infinity to infinity, a rho coordinate that goes from 0 to infinity, and some angular phi coordinate. And just as a note, if I instead took t to go from 0 to 2 pi, I would get this picture. But since I'm taking t to have all of its possible values, then that corresponds to taking the universal cover. And so this is ADS3. It's really just the universal cover of SL2R, and that's going to be very useful when we want to talk about string theory on it. And again, just a reminder, stop me for questions at any time if you have them. So now we want to consider strings on ADS3. And just as in any space-time, strings on ADS3 are going to be some nonlinear sigma model whose background is given by the ADS3 metric, as well as any fluxes that are present. And so the fundamental fields are going to be maps from some world sheet to the space-time of ADS3. The main difficulty, if you were to say try to do this for ADS4 or ADS5 or so on, is that in general, when you try to consider a string theory on some curved spacetime, that's a very difficult problem. In particular, quantization is very difficult. So it's very convenient in this case to instead adopt the perspective of ADS3 as being this group manifold. So instead of considering some map from your world sheet to ADS3, you consider a map from your world sheet to this group manifold. So your fundamental fields are group valued functions on the world sheet. And this defines for you then the embedding of the world sheet in ADS3. And due to the fact that this is a group manifold, one of the really nice things that happens when you consider strings on a group manifold is that the action is given by a Wess-Zumino-Witten action, which is sort of given by this kinetic term here, where you consider your field G, and then just take this bilinear of its derivatives, and then take its trace. There's also a part of the action which corresponds to the Nuve-Schwarz flux, which is important in the quantization of the theory, but I won't talk too much about that. And if you want to learn more about these things in general, just look up Wess-Zumino-Witten models, and this is a very general construction. And one of the very nice simplifications that happens, which is exactly analogous to what happens in flat space, is that the equations of motion for these types of strings has a factorization into left moving into right moving parts. So there's the equation of motion looks a lot like the 2D wave equation. Usual light cone coordinates on the world sheet. So you have some break into left and right movers, and that is in particular something that's going to help us a lot in quantization later down the line. All right, so now that we have an action and some sort of yes?
Is it possible to show this action is equivalent to the usual Polyakov action?
Yes.
I see.
Yes, so this is equivalent to the usual Polyakov action. This part here essentially being the kinetic term in the Polyakov action. One way you can see this is that these two derivative terms are valued in the Lie algebra. And when I take the trace of products of things in the Lie algebra, that's essentially the killing form on the Lie algebra, which is what we take as to be the metric in ADS3. So this is really just the Polyakov action. And then this Wess-Zumino-Witten term is actually just the integral of this two-form Calvert-Ramon field that we consider.
So the level K takes, is a K is a level?
Yes. So
it
K
takes
here, strictly speaking. Sorry, what?
So it takes only the integer value?
Typically, so if you have a compact group, then yes, K does have to take an integer value. But if you're working on a non-compact group, so like ADS3, you typically don't, you don't strictly speaking have to take K to be integer.
I see. And yeah. The level K corresponds to the string tension. Is it correct?
Yeah. So this is actually quite simple to see. So typically in the Polyakov action, the coefficient, so what's right here, coefficient here should look something like 1 over alpha prime, right? So you think of that, so you think of alpha prime as being sort of setting the string length. So it's something like the string length squared. And so 1 over K determines the string length for you, in particular in units of the ADS radius. So you think of 1 over K as being something like the string length over the ADS radius, potentially squared.
I see. Okay, thanks.
Yeah. And so very large K, then in the path integral, you see that saddles would dominate. And so this is some semi-classical thing. And so you can consider that as like a very short string. Whereas for small K, which is the tensionless limit that Matthias is talking about, is considering this K to be small. And so the string length is quite big. Other questions? All right. Yeah, so now that we sort of had this factorization of our solutions into left and right movers, we can start to actually study trajectories. And so first, I want to start out with some very boring solutions to these equations of motion, which are simply going to be particle trajectories. So I can take, for instance, as a solution, the function g of t to be something like this. So it's some 2x2 matrix, which looks just like a rotation matrix. So it certainly has determinant 1. And if you sit down and do some work, you can actually find functions gl and g right, which I don't know off the top of my head, unfortunately, at the moment, but you can find these functions g left and g right, which when put together generate this 2x2 matrix. And then you can multiply on the left and right by some constant 2x2 matrix with unit determinant. And the solution to these equations of motion you get looks just like a geodesic. So in particular, there's no sigma dependence. And so there's no length to the string. And so here you can consider some geodesic, which corresponds to just some massive particle moving around in ADS3. Similarly, you can instead consider some diagonal 2x2 matrix whose components also depend on tau. And again, there are functions g left and g right, which when put together produce this matrix and which are purely left and right moving. And then you can conjugate on the left and right by some constant matrix. And the solution you get looks like some space-like geodesic in ADS3. And these are quite boring trajectories, but they are sort of the starting point for what we want to discuss. So one question is, when we have these boring trajectories, is there a way we can use them to make more interesting ones? The answer is yes. There is an operation that we can use, which I'll call sigma, which, given some solution to the equations of motion, simply multiplies on the left and right by some particular 2x2 matrix, where here T3 is one of the generators of SL2R as a Lie algebra. So you multiply on the left by e to the w sigma plus T3, and on the right by e to the minus w sigma minus T3. And this is still a solution to the equations of motion because this leftmost part is just going to multiply GL. And what you're going to end up with is still a purely left moving component, and the right part will just multiply GR, which is still just a right moving component. And so this is some operation that takes solutions to solutions. And you can ask, well, what does this operation look like in our global coordinates? And in those coordinates, that's actually very simple. It takes the function t, which again is a function from the world sheet to ADS3. It's the coordinate of the world sheet, and adds a term proportional to w tau. And it also takes phi and adds a term proportional to w sigma. And particularly because phi and sigma are both periodic with period 2 pi, we find that this only makes sense as a solution in ADS3 if we take W to be an integer. And so these operations will kind of stretch out your trajectory in T by adding a component proportional to tau, whereas it will wind it'll wind your string W more times around the center of ADS3. So to sort of get some visualization for this, this will take our time-like geodesic and wind it around the origin a bunch. So it's just going to sort of fatten it up. It'll revolve it around the central axis, and you'll get a world sheet that sort of expands and collapses over and over again. And these types of solutions in ADS3 we call short strings. And for the time-like, or for the space-like geodesic, something interesting also happens, which is that because of this sort of stretching in time, so because of this adding this T plus W tau, we now see that the range of this trajectory is no longer finite in T, and so it really stretches from T equals minus infinity to infinity, and then it also winds around a bunch of times. So you end up with this string solution, which asymptotically in the past is very, very close to the boundary, and asymptotically in the future is very, very close to the boundary. But at some point in the present, sort of collapses to a point. And these solutions we call long strings. And this action that takes one solution to the other we'll call spectral flow. And this turns out to be the exact same spectral flow that Matthias talked about in his lectures. And so this is the sense in which spectral flow can be thought of as a winding in ADS3. It's sort of winding W times in the phi direction. And in particular for long strings, because they approach the boundary asymptotically as time goes by, you can think of this as sort of the winding number of a string on the boundary cylinder of ADS. But it is important to note that because of the fact that this cycle that they're winding around is contractible, I can always take this cycle and just shrink it to a point. Because of the fact that this is contractible, there's no topological obstruction to me changing the spectral flow or changing this winding number through some scattering process. In particular, spectral flow is not a conserved quantity. So if I were to consider, say, a 3-point function of strings in ADS3, all of which have 3 different values of W, there is no requirement which says that these 3 spectral flow quantities have to add to 0. And so some people will say that that this is some violation of winding number conservation. Really, it's just some other quantum number that's not conserved, but still looks a lot like winding when you view it from the boundary cylinder. Up to this point, are there questions? Because that's sort of the end of the classical story of strings on ADS3 that I wanted to talk about. All right. So let's move on to something a bit more quantum. And so here I'm going to just introduce and discuss in a bit more detail sort of the actual quantization procedure of strings on ADS3, the spectrum, the representations that can appear, and identifying some of the states in a dual CFT in some more detail. So let me just briefly remind you how this story works in flat space. So if I take strings on just the real line, or many copies of the real line, like Minkowski space, the typical quantization procedure in second quantization is as follows. You solve the equations of motion for x, and you then decompose x into some modes. So in particular, you take the derivative here of x. I actually don't need a Lorentz index. You take the derivative, so the holomorphic or left-moving derivative, and you decompose this into some kind of mode expansion. And here I'm just going to use complex coordinates. Right. And so this field on the world sheet has some modes, which you call alpha n, which are going to satisfy some algebra, which you call the oscillator algebra. And from this oscillator algebra, you can build Virasoro generators, which then satisfy the Virasoro algebra. And to quantize the string theory, you impose the physical state conditions on the states which lie in representations of that algebra. That's sort of the classic story of flat space string theory. And for ADS3, things are pretty much exactly the same. So there's a similar current, which looks just like del X. It's sort of the curve space analog of this current. And you can solve its equations of motion. The equations of motion just tell you that it's purely left moving or purely right moving. Again, you can decompose this into modes. You can find representations of this mode algebra. And then lastly, impose physical state conditions. And this should give you all of the physical states that can occur in the ADS3 string theory. Now, strictly, there's a bit more. You have to sort of prove that your spectrum has no ghosts, and that's actually very difficult and not something I'm gonna be talking about. And you have to show that your representations are unitary and all that. But for now, this is just the first steps that you want to take. So let's actually get started with it. So in flat space, this current is actually a conservation. It actually comes from a conservation law. So this current comes from the fact that in flat space, there's a symmetry, which is simply take x and shift it. There's sort of, flat space is homogeneous, and so you can shift any way you want. And on the world sheet, this gives rise to a conserved current, whose left moving part is del x, and whose right moving part is del bar x. And the equations of motion then tell you that del x is purely left moving or purely holomorphic. There's a similar symmetry. There's a global SL2R symmetry, which is I can take my field G, which remember is this SL2R valued field on the world sheet, and I can multiply it on the right by some element of SL2R. I could also multiply it on the left, and strictly speaking, that is a different symmetry, but the conserved currents that you get out of these two are related to each other, so you can really just consider only one. And so there's some conserved current, who, when you break into Z and Z bar components, is just, we'll call J and J tittle. And J is just going to be essentially the derivative of our field G, but now with this G inverse thing. So it's actually Lie algebra valued instead of Lie group valued. And J tittle is the same, except now the G inverse appears on the other side and you get an anti-holomorphic derivative instead. And because this current lives in the Lie algebra, you can break it into Lie algebra components, which we'll call JA. And so these are the currents that showed up in Matthias's talk, where here A is equal to 1, 2, or 3, or similarly, you can take A equal to plus or minus or 3, which is sort of a more convenient basis for a lot of the calculations we want to do. And the equations of motion, which remember determine that G could be split up into a product of left and right moving pieces, the equations of motion just tell you that JA is a purely holomorphic component, and J tittle A is a purely anti-holomorphic component. And so now, just as in flat space, we have this current. You can consider its mode decomposition. And this gives you a basis of operators which act on your states. And the mode decomposition is identical. And we call these modes JAN. And in this 3 plus minus basis, you can compute what the commutators of these fields are and turn that into commutators of the modes, and you get this algebra, which is some infinite dimensional version of SL2R. We heard these coefficients that show up. These are just the structure constants of SL2R, these ones. And then there are these central terms, which come with the level. Where here K is the same K that showed up in the action of the string on SL2R. And so this algebra we call SL2R at level K, and it's an example of an affine or Kac-Moody algebra, which are sort of the main mathematical objects that show up when you consider string theory on group manifolds. Okay, so those were the first two steps. Solve the equations of motion for the currents, decompose into modes. And so now we have the third step, which is to find representations of the resulting algebra. Because whatever states I'm going to have to fall into representations of this algebra. And the strategy for finding representations of this algebra is to note that if I take just the zero modes, so if I set m and n equal to 0, then the mode I'll get on the left-hand side in every commutator is also going to be 0. And so the zero modes among themselves form a closed subalgebra. And that algebra is exactly just SL2R. And really, you can think of these modes as sort of generating the global SL2R symmetry that acts on ADS3. And so because this is some subalgebra of the algebra we have above, any representation of this algebra has to also be a representation of SL2R. And so instead of trying to find representations of this guy, first ask yourself, how do we find representations of just SL2R? And the representations of SL2R are actually very similar to those of SU2. So they're labeled by some m, which is similar to the magnetic quantum number that shows up in SU2, as well as some j, which is like the spin that shows up in SU2. And you can parameterize the action of the SL2R generators. Here m we consider now to be the eigenvalue of J03. And J plus and minus now act as raising and lowering operators on J3, which we can see just by the form of this OPE, or of this commutator relation. And notice that within one representation, if I take some state and I act on it with any of my generators, two things are invariant. One, the value of J is invariant. And two, because m only differs by an integer, the value of the fractional part of m is invariant. So any irreducible representation has to have constant values of those two quantum numbers. And depending on what values you take, you get two types of representations, which we'll call continuous and discrete. Continuous representations are those where I take the fractional part of m to not be related to the fractional part of j at all. which basically means that these two coefficients can never be zero. And so by acting with J0 plus or minus on any state, I can always sort of increase or decrease the value of M as much as I want. And that gives me an infinite tower of states that I can consider in this representation. On the other hand, if, say, the fractional part of M is equal to the fractional part of J, then this coefficient can vanish for J minus. And so in particular, the state JJ is annihilated by J minus, which you can just see by the form of this action. And so you have an infinite tower of states still, but they only it's only infinite in one direction. So we call this a discrete representation for historical. The discrete plus representation, which comes when sort of the J minus component can kill one of the vectors. But when J plus can kill one of the vectors, so if in particular I take the state minus JJ, J plus will kill it, so there's nothing here. But I can still act with J minus to create sort of an infinite tower of descendant states in this representation. Now, of course, there's also a trivial representation, and there are a couple other weird types, but for the purposes we need to consider now, these are all the types of representations of SL2R that matter. So now, just as so a typical trick now that we have a representation of SL2R, we can turn this into a representation of the full infinite dimensional algebra SL2R sub k by considering the same states, Mj, but now demanding that they are highest weight states, so that they are annihilated by all modes of J, which are positive. And then now, if I just consider this state plus all of its descendants, acting on these highest weight states Mj, then this gives me a representation of SL2R sub k. And so in this way, I can take, say, these continuous representations and turn it into some representation of SL2R sub k, which I'll just denote with a hat. And I can do the same for the discrete representations, and you get representations which are, again, denoted with a hat. And I should note, even though I haven't written it anywhere, that these continuous representations, this is sort of related to this analysis of Maldaceno-Oguri. They show that these continuous representations, if you look at their spectrum in the space-time, these look like long strings. And these discrete representations look like short strings. So sort of the physical meaning of these continuous and discrete representations is that they correspond to these pictures that we drew earlier, sort of in a semi-classical kind of way. In particular, this works out if you take K to be large and analyze the spectrum. It looks like the energy of a short string, or it looks like the energy of a long string. But as we know, because of Matthias's lectures and also because of this winding picture, that these aren't all the representations that you can consider. And in fact, there's a spectral flow automorphism which acts on the currents and which can generate new representations for you. So if I take this action from way up here, so this action sigma W, if I act on G, well, since I built currents out of G, I can ask, okay, well, what is the action of sigma W on the currents? And this is exactly the it's exactly the expression that Matthias talked about in his talks, where the plus and minus currents just get affected by having their mode shifted up or down, respectively. And the J3 current is unaffected except for its zero mode, which gets shifted by a constant. And when we say that this is an automorphism of the algebra, what we mean is that this preserves the structure of the commutators. So if I take the commutator of the spectrally flowed images of two currents, it's just the spectral flow of the commutator of those two currents. And as an example, I'll show you how this works for, say, the J plus J minus current. So you can consider the commutator of the spectral flow of the J plus J minus currents, but we know how spectral flow acts. It just moves the mode numbers down and up. And because we know the form of the SL2R algebra, we know what this commutator is. It's minus 2 J3, and the mode is going to be the sum of the two mode numbers, but that's just M plus N. And then plus K M minus W delta of the sum of the two mode numbers, which again is just M plus N. So here I'm just using this commutator here. Then you can rearrange this slightly. This is minus 2 J3 M plus N plus KW over 2 delta of M plus N 0 plus KM delta M plus N 0. And then this is clear that this is just by the form of spectral flow. This is minus 2 times the spectral flow of J3 M plus N plus the central term, which is just the spectral flow of the original commutator for J plus J minus. And now as an exercise, if you wanted to sort of get your hands dirty and get used to this kind of stuff, you can use sort of a similar technique to show that sigma W is an automorphism of the full algebra. So not just considering, say, the J plus J minus commutator, but considering the J3 J plus commutator and the J3 J3 commutator as well. Although these two are easier, so I've really done the hard part for you. Now, given a representation, so representations we've already considered, we can take a state and also spectrally flow it, which means just adds a label to tell you that it transforms in the W spectrally flowed representation. So the label just tells you how its transformation law changes. And the transformation law of a state in the W spectrally flowed sector is that if I take the operator A and I act on this state, then I spectrally flow the operator, act on the state, and then keep my label because the new state is still in the W spectrally flowed sector. And so in this way, while classically, spectral flow was something that took you from classical string configurations to classical string configurations, Quantum mechanically, it's something that takes you from, say, some representation, which we can start out with some highest weight representation, and then takes you to some new representations, which are often non-highest weight. Yeah. Questions up to this point?
Yeah, I don't.
All right. Oh, yes.
Yeah.
Sorry?
Sorry, I was just saying that I don't see any questions. But
oh, okay. Okay, sorry. Yeah. Great. All right. So those are we're almost done with the sort of full quantization procedure. Now we just have to impose the physical state conditions. And so to impose the physical state conditions, we need Virasoro modes. So remember that in flat space, you still have these modes, and from these modes you can construct Virasoro modes LM, which are sort of just given by bilinears of the alpha modes. And if I have Lorentz indices, I just contract them by sort of adding whatever metric I have. And I can do the same thing for SL2R, and this is known as the Sugawara construction, which is sort of generally how you can define Virasoro modes in any model of string theory on a group manifold as bilinears of these conserved currents. And the Sugawara construction tells me that if I want to find the Virasoro modes on ADS3, well, I have some funny prefactor, which depends on the level. And then the rest is given by sort of bilinears in these currents, sort of in the same way that the Virasoro modes are given by bilinears of the currents in the flat space story. And this bilinear is exactly the metric on SL2R. So this is sort of given by the killing form of SL2R contracted with these currents. And of course, as always, I need to be careful about normal ordering, but that only matters when I take m equal to 0. And so now that I have a Virasoro generator, I need to impose that the Virasoro generators annihilate my states for n positive and act to give me 1 with the L0 mode. Now, if I were doing superstring theory, this would be a bit different, but right now I'm just doing everything bosonic, so there's no need to get fancy with it.
So you mean psi equal to psi, right? When you mean 1?
Oh, yes, sorry. Yes, absolutely. Thank you. Yeah. 1 is the eigenvalue, obviously. Yes, thank you. And these Virasoro generators, well, you consider just ADS3, but in general, you're going to be considering spacetimes that are ADS3 cross M. And so the Virasoro generators are in general going to break down into one ADS3 component and one component coming from the rest. So whatever 7-dimensional, 23-dimensional manifold you want to consider as sort of the rest of your spacetime. And so as one exercise, you can show that if I take these states MJ, which are my highest weight states in my ADS3 or in my SL2R model, if I take these states and I just take the zero mode of my Virasoro generators, then they act to give you the following eigenvalue, which is proportional to this crazy coefficient, and then also this term in terms of the j's. And actually, I got that wrong. It should be j times 1 minus j. And this J1 minus J is actually the quadratic Casimir of the representation whose spin is given by J. And so now, if you want to find physical states on the world sheet, the recipe is clear. Well, we want to consider spectrally flowed representations. And so you can ask, given a state, which is some spectrally flowed highest weight state, tensored with some stuff in this in the internal CFT, you can ask what values of M make this state physical. And the reason that we want the value of M is that these zero modes J30 and J plus and minus 0, these generate SL2R. They generate the global SL2R transformations of ADS, which are also to be identified with the SL2R transformations of the dual CFT. So sort of the global 2D conformal symmetries. So in particular, this is J3 is to be identified with L0 of the dual CFT, and J plus or minus are to be identified with L plus or minus 1. And which one you pick for which is a matter of convention. So if you want to identify the spectrum of whatever CFT that you potentially have living on the boundary, the spectrum is going to be given by the eigenvalues of J3. And if I take J3, let me write this up here. I didn't really give myself much space here, did I? If I take J3, acting on some spectrally flowed highest weight state, its eigenvalue is just M plus KW over 2 MJ. W, and this combination I can call H. And I'll even put a little subscript W on it to remind me that it's in the W spectrally flowed sector. And these eigenvalues are going to be exactly what you identify with when you talk about the spectrum of the dual CFT. And so if you want to identify the spectrum of the dual CFT, like I said, the question is clear. You take a general state before imposing physical state conditions on your world sheet, and you ask for what value of M, equivalently for what value of H, is this a physical state? So what states are going to appear in my dual CFT? And for this, you need to know what the transformation laws of the Virasoro modes are under spectral flow. They're just given by the Virasoro modes plus some term proportional to J3. And then specifically on L0, the normal ordering constant also gets shifted by this constant here. And so we can actually work this out. So the ADS3 generator acting on this state is just going to be given by this mess acting on the unflowed state. So in particular, we know what L0 is acting on the unflowed state. It's right here. So there's this J1 minus J over K minus 2. And then minus W, and then the J30 eigenvalue, which is just M, and then minus KW squared over 4. And so that's the eigenvalue of the state under a L0 of ADS3. And, well, like I said, we don't really want to work with M here. We want to work with the conformal weight of the state in the dual CFT. And so we can just make a very quick change of variables and write this in a slightly different way. Minus WHW plus KW squared over 4 times the state MJ W. And so this is the world sheet conformal weight of this state. And as I said, physical states have to satisfy that L0, the L0 eigenvalue is equal to 1. So in particular, this tells us that J, 1 minus J over K minus 2 minus W HW plus KW squared over 4 plus whatever the conformal weight is of this state with respect to the internal CFT. I'm assuming that it's highest weight in the internal CFT as well. This is equal to 1. And so this is just some linear equation, which is very easy to solve, and you can solve it for HW. And I mean, you could work through that. At least for H1, I'll write down the answer explicitly. Actually, no, I'll just write down the answer for HW. So this is just 1 over W J, 1 minus J over K minus 2 plus KW squared over 4 plus delta M minus 1. And this formula doesn't seem super enlightening at first, but you can show, and it's a 2-line exercise in algebra. You can show that if you know H1, then you can work out the rest of them by just dividing H1 by W and then adding this contribution, which is proportional to K and then has some funky dependence on W. And in particular, if you take K equal to 1, which is sort of this tensionless limit that Matthias has been talking about for all week, if you take K equal to 1, you notice that this coefficient here disappears, and you're left with the fact that the W spectrally flowed state, or the state corresponding in your dual CFT to the W spectrally flowed highest weight state, just looks like the conformal weight of the first spectrally flowed sector divided by W plus this term. And this term is exactly, as Matthias mentioned, this is precisely the ground state energy. This is the ground state energy of the W twisted sector. Of the symmetric orbifold of whatever you want. And that's really the whole quantization procedure for strings on ADS3, up to identifying the physical state condition. Of course, we still have to prove that there are no ghosts in the spectrum, but if you really want to go through that, you can defer back to Maldaceno Nogori in that original paper. But up to this point, are there any questions? I mean, really, this part was just what Matthias talked about, but in just sort of painstaking detail.
So this statement about, like writing it in terms of H1, like what's the worldsheet interpretation of this? Like how should I interpret the statement? I mean, this is a true statement, I understand that. What is why would you expect such a statement to be true in the first place? Mm-hmm. Is there some way to guess?
Yeah, so for instance, so it makes a bit more sense if you consider a specific theory that you're taking the symmetric orbifold of. So for instance, if I take the symmetric orbifold of T4, then states, let me just go down all the way. So if I just take the symmetric orbifold of T4, in the W equals 1 twisted sector, this is just the identity twisted sector. So it just looks like states on T4, and I get states which look like, say, alpha minus 1, or let's be even more general, alpha minus N1, alpha minus NL acting on some vacuum state or something. Or this can even have some winding, something in the Nurian lattice. Then the conformal weight of this, so the conformal weight of the state is basically going to be proportional to n, which is the excitation number here. There's also going to be a part which is given by this, the winding, but let's ignore that for the time being. Let's really just assume I'm considering a state that has zero winding to make things, zero winding and zero momentum, just to make things less complicated. So the conformal weight is just going to be given by n. But if I consider the W twisted sector, the corresponding states are going to look something like this.
Sorry, the above thing is for W equal to 0. Or
the what?
The thing that you wrote down, this h going as n, is for W equal to 0.
No.
Okay, this
is for W equal to 1. Okay. Yeah. So in the symmetric orbifold, W here is going to label the length of a permutation. And if I have a permutation of length 1, that's the identity permutation. So this is equal to this is the untwisted sector of the symmetric orbifold.
Right, okay.
Yeah. So now if I consider generic W, then my states are going to look like this, where now my oscillators are modded, but are fractional with respect to W. And I don't act on just the vacuum, but I act on the W twisted sector vacuum. So H is going to look like N over W plus the H of the vacuum, which one can work out in the symmetric orbifold. And it's given exactly like this. And so this is precisely the form of spectrum that we had, or that we just looked at above in the string theory. Or
H1 over W.
H1 over W, yeah. Exactly. And so this is sort of the first hint that the dual CFT is going to look something like the symmetric orbifold theory. And in particular, this is a good hint that k equals 1 is sort of the right thing to do.
Okay.
Other questions? All right. So it looks like I might be a little short on time, so I will try to go through this next part a little more quickly so that I have more time for generic question answer time. I might leave about 15, 20 minutes for that. So now I just want to briefly discuss this free field realization, but since Matthias went into a decent amount of detail on it, I want to mostly just given as an opportunity to give you guys as exercises or give you an opportunity to get your hands dirty with this stuff, but I'll work out a couple things. So as Matthias mentioned, when you're adding supersymmetry, and so now we're looking at backgrounds, which are ADS3 cross S3, because those are the backgrounds that appear as near horizon geometries of certain brane systems, and you want to add supersymmetry, you can either add supersymmetry on the world sheet, so adding superpartners to your currents, and the resulting model looks like an SL2R algebra with k going to k plus 1 or k plus 2, and an SU2 algebra where now k is shifted down to k minus 2, and then 6 free fermions, which are given by the superpartners of these guys once you decouple them. And the problem is that this breaks down at k equal to 1 because I have some Wess-Witten model of a compact group with negative level. And that's not good. And then there's a second possibility, which is instead to work with the Wess-Witten model on a supergroup. And the sort of vague motivation here is that if I consider the superspace of ADS3 cross S3, it can be given as a product of two copies of this supergroup PSU112, which I can think of as belonging to sort of the left moving and right moving strings, modded out by this global symmetry of SL2R cross SU2. And so one might think that sort of the natural thing to consider a Wess-Witten model on once I take to superspace is the supergroup PSU112. And a similar logic actually works for ADS5 cross S5. And sort of the magic of this alternative formulation, which is the hybrid formalism, the magic of this formulation is that it works perfectly at k equal to 1. There's no problem with k equal to 1. And so at k equal to 1, which is this tensionless limit that we want to consider, this is sort of the honest way to work with the string theory that doesn't require a lot of hand waving. So the supergroup PSU112, like any supergroup, is given as a block diagonal form, where in the diagonal blocks, or is given by a block matrix, where in the diagonal blocks, you have some normal elements of standard Lie group, so in particular SL2R and SU2, which are going to correspond to ADS3 and S3. That said, I'm going to ignore this part, and this part right now and focus just on the SL2R part, since that's the part that really captures the dynamics of holography. Really, the ADS3 is really what matters in having a holographic theory. And so, as Matthias mentioned, at k equal to 1 exactly, the algebra PSU112 at level 1 has a realization in terms of free fields. And again, I'm going to focus purely on the bosonic part, but if I included fermions, you can construct the SU2 purely out of the fermions, and then the supersymmetry generators would be sort of combination boson fermion bilinears. But I digress. At so the free field realization at k equal to 1, if we focus on just the bosonic part, is given by 4 spin half bosons, which we'll call psi plus and minus and eta plus and minus. And if you wanted to sort of write out the action for these guys, you can certainly do that. It looks something like this. It's a terrible psi. And then, of course, actually, I think this might be a, yeah, this is an anti-holomorphic derivative. And then, of course, plus the complex conjugate for the right moving components. And because these are spin half, that means that the conformal weight on the world sheet is 1/2 0. And so these are purely holomorphic fields, which have a mode expansion whose modes are half integer moded. And you can write down the algebra that they satisfy, and it looks like this, which is really just 2 copies of an oscillator algebra. And out of these bosons, you can construct some bilinears, which we'll call J3 and J plus and minus, which one might guess by their name actually satisfy the algebra of SL2R at level 1. So, and of course, just to reiterate what that algebra is, it's this. And just to give an example of say how you might show this, and I'm going to do the easiest example because it's the easiest one to not mess up during a talk, is let's just take this at face value and try to compute the commutator of say J3 with J plus. So what I mean when I say take the bilinears here is that if I want the M mode of say J plus or minus, this is given by a sum over R, where here R can be integer or half integer of xi plus or minus M minus R, and then eta plus or minus R. And there's no need to normal order because the things I'm taking bilinears of, at least in this case of the J plus and minus modes, actually commute with each other. In the case of J3, you actually do need to consider normal ordering. But since we're considering a commutator where J3 is in the commutator, the normal ordering constant actually won't matter at all. Because it'll just appear inside the commutator as a number, which doesn't contribute. So we can, actually I'm feeling I did not give myself enough room for this. So I might have to do it on another page. Let's go down here. So I want to compute this commutator. Well, I need two sums over some modes. J3 is defined with a -1/2 out front. This is going to give me xi plus of M minus R, xi eta minus of R plus xi minus M minus R, eta plus R, and then that's going to commute with xi plus S, or xi plus N minus S, eta plus S. Okay. So this is -1/2. This sum. And then we can break this up into two terms. One of which is this, and the other is this. And now we can use a commutator identity, which I always forget, so I can just derive it briefly. Plus A, C, D, B. Great. Okay, so I can use this commutator identity to say break up these terms. Yes, I'm kind of regretting not having written this down first, because this is more tedious than I had expected when when planning. But nevertheless, so this first term we can break up into two commutators, an eta minus r. And then you can similarly do this for the second term as well. All right, so now we have a sum of 4 commutators. And let's look at them individually briefly. So this is just psi plus times some commutator of eta minus with a psi plus and an eta plus. Now, one thing to note is that eta plus inside of this commutator commutes with everything else inside of this commutator. So we can actually just pull it out to the right. And similarly, although I feel no, this is fine. Similarly, oh, what did I do? There we go. Had a brief malfunction with my iPad. Similarly, this commutator vanishes because nothing in here pairwise has a non-zero commutator. So the second guy is just 0. Same for this third guy. And then the fourth guy, again, we see that that here psi plus commutes with everything else. We can just pull it out to the left. And so we're left with a pretty drastic simplification. Which is again a sum over R and S, psi plus M minus R, and then the commutator of just psi minus with of eta minus with psi plus, which just gives me a minus sign, and then a delta function on their modes, R plus N minus 0, or R plus N minus S, comma 0, and then eta plus S. And then the second part, I can use the same logic. You just pull out psi plus to the left. And then you're left over with the commutator of psi minus with eta plus, which is just -1 with this delta function. M minus R plus S, comma 0, and then just the eta plus. And then if you just pull out the minus sign, you see that both of these terms is just a normal order product of psi plus with eta plus, psi plus with eta plus. And so you're left out with just with nothing but J plus M. That's all that you're left over with, because that's the only thing that a normal order product of psi plus with eta plus can possibly be, since they commute with each other. Yeah, I apologize for how tedious that exercise was. I had planned for it to be a 2-liner somehow, but the exercise now, if you guys want to get your hands dirty, is to really show that the rest of these commutators also hold. So the rest of the SL2R algebra is obtained in this way. And so that's done, and the exercise to show the rest of them. But you do have to look out for normal ordering, because the rest of them will have this sort of central term on the end. And that comes exactly from normal ordering when you do the commutators. All right, questions on that? Sorry for that being as tedious as it was. Great. Just really wanted to convince you guys that this free field realization actually does work, and it does give you SL2R. However, as was mentioned, it gives you more than SL2R. So if I take just Xi plus and Xi minus, they're bosons, so they commute. So if you count the number of bilinears, unique bilinears that you can form out of them, you'll find that there are actually 10. Whereas the bilinears we've written down for SL2R, there are only 3 of them. And so the question is, well, if we want to just describe ADS3, we really should just be describing SL2R, but it seems like we have a theory that has far more going on than just SL2R. It has 7 extra currents. And the way to get rid of these, which is what Matthias described for you, is to take another current, so one of these extra 7 currents, which is called U, which looks exactly like J3, just with the wrong sign in the middle. And U has the following properties, that if I take the commutator of U with any of the JAs in SL2R, I get 0. So the SL2R bit of this construction is uncharged under U, and every other current that you can possibly make is charged under U. So if you demand that all physical states have 0 charge under U, so in particular you demand this physical state condition, which is that UN on these states is equal to 0 for all positive or for all non-negative nodes, then the only physical states you could possibly have by building on some already physical state is by acting with SL2R excitations. Those are the only things that are uncharged with respect to U. And so by imposing the physical state conditions for U, you now take these 10 bilinears and you've really gotten rid of 7 of them. And the only excitations that you can have to construct physical states out of other physical states is to act with the SL2R currents. And so that's how you get just pure SL2R out of the symplectic boson theory. And if I had also included the fermions, then there's another current which looks similar but with the fermions, and you have to gauge out by both of those. But for now, since we're just looking at bosons, this is as complicated as it gets. All right, and the sort of final thing I wanted to touch on in regards to this symplectic boson theory is sort of constructing the representations in detail. So, or in a bit more detail. So we have this algebra of our symplectic bosons, and this is supposed to give me some kind of string theory, where the string theory is I take this action, and then through some kind of gauging procedure, I gauge out this combination, the current associated with some extra symmetry, and I gauge out that symmetry, and I'm left over with some theory, and so my states have to transform in representations of this algebra, and then I annihilate any state which doesn't satisfy the physical state conditions. And so in particular, let's consider just the R sector, because the NS sector is somewhat boring. And in the R sector, the 0 modes have some non-zero commutators, which I'll remind you in flat space string theory doesn't happen. The 0 modes in flat space string theory commute. And so the highest weight states here are going to satisfy some are going to live in some representation of the zero mode algebra. And the way you can quantize this algebra very easily is by noticing that the algebra obeyed by the zero modes is just an oscillator algebra, simple harmonic oscillator, where you consider, say, psi plus here to be a raising operator and eta minus to be some lowering operator, and similarly for eta plus and psi minus. So you can work just as with the harmonic oscillator, and you can introduce now two labels which get raised and lowered, where here psi plus and eta minus respectively raise and lower M2, and eta plus and psi minus respectively raise and lower M1. And these coefficients out front are just there to make sure that the commutation relations are obeyed and are normalized to 1. And then in this basis, so this sort of oscillator basis for the symplectic boson algebra, you can ask what are the actions of the SL2R currents on the states M1 and M2. And you can work this out quite easily. The action of J3 is just going to be, showing the action of J plus and J minus is going to be easy because that's just, say for J plus, it's just acting with psi plus and then acting with eta plus, which you can see should raise M2 and then raise M1, and you're left over with the coefficient 2M1. And for J minus, it's the same. You act with psi minus and then eta minus, which is just lowering, lowering, and you are left over with 2M2. Probably have a sign wrong there, potentially. But in our usual sort of MJ basis of SL2R, this would be M. It's just the eigenvalue of J3. And then you'd have to identify, say, 2M with M plus J. And yeah, that was a wrong minus sign. And 2M2 with M minus J, so that the actions of J plus and J minus are normalized. And you can show yourself that this is the case if you identify M with M1 plus M2, obviously, and J with the difference of M1 and M2. And so as an exercise, if you want to get your hands dirty, is to show that, for instance, the J3 action really does take this form. And then finally, the action of U0, once you've worked out, say, the action of J3, since it's basically the same exercise, is easy to determine. And it's just M1 minus M2 minus a half. That's the eigenvalue of U0 under these states. And so taking the physical state condition U0 equal to 0 is simply the same as taking the state condition, or simply the same as picking out only those states with J equal to 1/2 as physical states. So your J equal to 1/2 is a physical state condition. And that's sort of the meat and gravy of how this spectrum truncation occurs when considering the tensionless limit. You only end up with physical states that have J equal to 1/2. Questions at this point? All right, and the very last thing I'll discuss before I get into sort of a general question answer session is just briefly remind you how spectral flow works and then invite you to do a couple of exercises. And of course, these slides are going to be uploaded, so all of these exercises and examples are going to be there after this recording. So The very nice thing about the symplectic boson theory is that spectral flow is sort of as simple as it can possibly be. Namely, that spectral flow just acts on the modes psi plus and minus, as well as eta plus and minus, by raising and lowering the modes by W/2. And through a miracle of mathematics, this exactly reproduces the spectral flow acting on SL2R. And as an example, I'll work it out for J plus or minus. This is just going to be sum over R of sigma W of psi plus M minus R, eta plus R. But of course, spectrally flowing the product of two things is just spectrally flowing them individually. This is sum of R. Eta plus or minus, I guess, M minus R minus plus W/2. Then eta plus or minus R minus plus W/2. And this is exactly the form that J plus or minus has, except the mode that you get out, which is the sum of these two modes, is just M minus or plus W. And this is exactly the spectral flow as it acts on J plus or minus. And as an exercise, which again is going to require some tedium in normal ordering, is to show that sigma acts on J3 the way that we know it does in SL2R, but also, probably more importantly, to show that sigma completely leaves the U1 current U alone, so that there is so that spectral flow sort of respects the fact that you're gauging out this U current, so that if I take a representation and I spectrally flow it, the spectral flow of physical states are still going to be physical, at least from the point of view of this gauging. They might not be physical from the point of view of the Virasoro algebra, but at least they'll still be physical from the point of view of gauging. I guess I wrote that twice. So yeah, as an exercise, you can show that this is the case. And then as one last thing, I want to mention that the symmetric or the symplectic boson theory differs from SL2R in that this is not the only spectral flow that you can consider. So basically what I mean by that is that the symplectic boson algebra is something like this. It factorizes into two algebras. So one of them is just the commutators between psi plus and eta minus, and the other one is between eta plus and psi minus. And so one can ask the question, well, why can't I spectrally flow these independently of each other? So why can't I choose to just spectrally flow this one or just spectrally flow this one? And the answer is you can. The only problem is that new spectral flow, which comes from spectrally flowing, say, just this one, won't satisfy or won't respect this gauging condition. That said, there is a spectral flow operation, which say will act like sigma W on this side and sigma minus W on this side. And this spectral flow we'll call sigma hat W. So it acts in opposite directions on each side. And as sort of an exercise, if you wanted to do it, because this spectral flow operation actually does show up in, say, the calculation of correlation functions, is to show that sigma hat acts on the SL2R generators trivially, but it acts on the gauge generator in, I want to say, I don't know, something like this. And I'm not sure about the sign or the normalization of that coefficient. But basically, you get a second spectral flow, and together this spectral flow and the other one form a basis of all spectral flow operations on this algebra. You get a spectral flow which acts trivially on the SL2R part, so is invisible from the point of view of ADS3, but has the property that sort of moves you around in sort of this extra gauge direction. And that's roughly everything I wanted to talk about in this tutorial session. So if there are any questions first off about that.
Are there any questions, comments?
All right. Well, if there are any questions about this specifically, then I open the floor to just a general Q&A session. Sort of about anything that I've talked about or that Matthias has talked about. Let me erase some of this stuff so I can have room. Or maybe I'll keep that. So yeah, I open the floor to general questions and about anything Matthias has talked about or what I've talked about today. And also thank you for your attention over the last hour and a half.
Okay, I don't see any questions. Okay, good. If there are no further questions, let's thank Bob Knighton again for, giving us this tutorial in a very, untimely time for him. So thanks, Bob, and we will meet again for the last tutorial of this day and of the school at 7:30 in Indian time for Surjit Rajendran's tutorial. Okay, thanks everybody, and have a nice day.
Thank you so much.